Hi everyone, it's Dr. Myers. This is a video to follow up the Theory of the Firm lecture that I did uh, for our class online. And part of that, a fairly small part of it, but a part that can be very confusing, used some very simple calculus derivatives. And we want to try to talk through here, as quickly as we can, as efficiently as we can, with what kind of derivative is going on here? What are we doing? And how can we kind of understand it and maybe even kind of control it? I don't think it's very difficult to learn, so we're going to give it a shot, and I hope this helps. So over here on the right or the left side, you see quantity is equal to a function of price. Q equals F per n, P per n. That's all it says. Quantity is a function of price. If price changes, quantity changes. And we typically think of this as a demand. And in order to find out how quantity changes with price, we go to the next line here, which is the one now in a red box. We say, if price changes, how does quantity change? And we might do something like Q2 minus Q1 over P2 minus P1, those being 2 points on the demand curve. Well, here's an example of a demand curve. Q is equal to 200 minus 5P. And I could take that formula and I could try different prices and I could lay out a table. And then I could do changes in price. The first change in price, which is an increase in by 10, is just 20 minus 10, and then 30 minus 20, and you can see price is rising by 10. And when we look at the change in quantity, quantity is falling by 50. So let's take that and actually graph it. So there's a demand curve, and that demand curve shows a relationship that if price were 40, nothing would be bought, and if quantity was 200, price would be 0. And you can figure that out by going up and saying, what if price were 0? 200 minus 5 times P is indeed 0. Well, that's a very mechanical way to do it. It's the way we do it in our examples. But there's another way, and that is by using a derivative. So a derivative is the same looking thing here, if you will. Let me show you that the derivative of Q with respect to P, and that's how we say it, it's dQ over dP. The derivative of Q with respect to P is actually equal to, in a way, I'm going to leave a little space here you can see, change in quantity over change in price. Now, what's the real difference? Well, the difference is that economists rarely work with very small numbers, and a derivative is a very small number. In fact, it talks about a change that is so small that it approaches 0. So the way we write this is that this is the limit. The derivative, dq dp, is the limit of change in Q over change in P when change in P approaches 0. In other words, a derivative is a change that is infinitesimally small. And indeed, we're talking about a change that occurs at a single point. Now, again, economists tend to look at prices not at a single point, but you look at changes over, bigger ranges like 10% increase or 5% sale. And the calculus, though, is where the change in Q over the change in P comes from. And we can define a derivative then as the slope of the linear line here that we started out with. We start out with a linear demand curve, and then we want to take the derivative of that. Well, dq over dp equals the change in 200 minus 5p as price changes. So that's just rewriting Q and putting that form in. But how would we solve this? Well, because we have a linear relationship there, there's a minus sign here, or a plus minus 5, we would have d200 over dp minus 5 dp over dp. Now the last term, it may take a little bit to get there, but what are we saying? We're saying d of minus 5p over dp is what? Well, let's go back to the first term, this one here. How does 200 change when price changes? Well, it doesn't change at all. 200 is a number. It's a constant. So no matter how price changes, that number stays 200. So the first part of our answer is 0. Now we have to deal with the other part, which is down here in this corner, which I now just put some brackets around. What is the change in minus 5p as p changes? Well, as it turns out, minus 5 is a constant. And to take the derivative of a constant times a variable, it's equal to the constant, which is minus 5, times the derivative of the variable with respect to, and what's odd here, it's respect to the same thing. So how does p change with p? It's 1 to 1. If p goes up by 10, p goes up by 10. So those cancel. And we're left with the other part of our answer, minus 5. So the slope of this equation, q is equal to 200 minus 5p, is minus 5. Now over here on our regression line, our slope is the rise over the run, if you remember that, except this slope is the dp dq, and it's equal to 40 minus 0. Since it's a straight line, we'll just use that entire rise over 0 minus 200. You got to go from the same point to the same point. So if I go from 40 minus 0, I have to go from 0 minus 200. And what does that give me? It gives me minus 40 over 200, or minus 1 over 5. And just notice that the slope, the way we draw our graphs, P and Q, where P is on the vertical axis, is a little different than the way we draw our demand curves or write our demand curves, which is Q as a function of P. So let me pause right there and let's think about it, and I'll come back with another example here in just a second. So on this screen you see the total product curve that we're using in our example, and written with letters for coefficients, it's Q equals B times L plus C times L squared plus D times L3. Now that's a cubic function, linear in parameters, and we can actually, analyze this, take the derivative and so forth. But before we get there, that function that was given to you was given with parameters, and that's written in the second statement. Q is equal to 50 times L plus 30 times L squared minus 1 times L3. So B is equal to 50, C is equal to 30, D is equal to minus 1. And we can take that and put it into a table. I've asked that you do this in Excel. So you'd write labor, 0, 1, 2, 3. That's all we're going to do right here. And when labor is 0, all of the terms are 0. 50 times 0, 30 times 0 square, and so forth. Q is 0. But when you let L be equal to 1, it turns out to be 49. When you let L be 2, and you do the math, get your calculator out, L to the third, and so forth, it's 132. And that's why I ask you to do in Excel to do the formulas. So if you write the formula, it'll automatically do all that calculation for you, and you can actually pull this labor down to 18 and the quantity down to 18 units of labor, and so forth. Now, if we go through here and we look at our changes, again, we're focusing on derivatives, so that's slopes. It's all derivative is. So we're looking at change in labor and change in quantity. What's the slope between those two things if we were to graph labor and quantity? What would we find? Well, we find labor is changing by 1. It's increasing by 1 each time. And quantity, change in quantity, is increasing, but not by 1 each time. It's increasing first by 49, then it's increasing by 132, or to 132 from 49 to 32, which is 81, from 132 to 243, which is 111. And that change, which is different than what you should be finding in your Excel, is because we started, take the first one, we started at 0 and we went to 49. Well, you could probably quickly see if we went from 40, if we came back down, our unit at 1 could have been 132 minus 49, and we would have written an 81 in the first place. So I give you a method in the Excel example where the actual answer is 66. Now, how did I get 66? I took 132 and I subtracted 0 for my change, and then I divided it by a change in labor, which now is 2. 2 units of labor gives 132, 0 units of labor is 0, and that's that one. And then on the next, the very next, I look at 49 and 243, and I look at that change, divide that by 2 units of labor, and what do I have? I have 97. Now, why is that significant? Because when we do the actual total derivative, or the derivatives here to find the slope, the answers turn out to mathematically be precise, and they are 67 and 98. Wow, we're almost on top of it. Our Excel emulated that, but only if we use this method, not if we use the other. So I've taken and written the expression between L equal 3 and L equal 1, and quantity 243 minus 49, and you can see how I did the changes here, and I came up with my 97. But to understand this, from a calculus point of view, we have to take the derivative. To do the derivative of the expression at the top of the page, we have to know some rules. And they're very simply applied. But here they go. The first one is, if y is equal to a, where a is understood to be a constant, and if a is a constant, it doesn't vary with x. So the derivative of y, how much does y change when x changes? 0. Y will stay at a, so it doesn't change at all. So what if y is equal to x? How does y change when x changes? And if you noticed, I had that backwards, so I rewrote it. Change in y over change in x, when y is x, it's a one-to-one relationship. Every time x changes, y changes. So there's a second derivative rule that we can use. But this one actually has sort of a hidden thing going on it. And I want to show you one more, and then we'll go back to that. And the one I want to show you is this. Y is equal to x to the power a. So a could be x to the 1, x squared, x cubed. Doesn't matter. A is just some constant. So remember, we're using letters A, B, C, and D just to be constants. They have nothing to do with y, nothing to do with x. They just happen to be in there. So dy dx, how does y change when x changes, when y is equal to x to the a power? Well, this is the formula here, which you can see as ax to the a minus 1 power. So in this case, it depends upon what the value of a is. So let's go back up and look at our first one. Our derivative, or our second one here, y is equal to x, our derivative comes out to be 1. We say it's a 1-to-1 relationship, but it's because this is x to the first power. So we bring down the 1, and x to the 1 minus 1, well, that's 1 times x to the 0. Anything to the 0 power is 1, and that's 1. So that kind of proves that, but it also lets us do this, x squared. So dy dx equals 2. See, we bring the exponent down in front of the expression, and then we have the expression that's left, x to the 2 minus 1, or just 2x. Y is equal to x3. Well, that one's going to be, bring down the 3, x to 3 minus 1, and we're going to be left with 3x squared. So to our problem, q is equal to this expression. And I put the constants in because it gets confusing when you look at a's and that sort of thing. But when you put the constants in, we know what they are, 50, 30, and minus 1. Now we take the derivative with respect to q, or derivative of q, I'm sorry, with respect to L. We always say with respect to what's on the bottom. That is, the question is, how does that total product curve change when we add more labor? Well, you saw above that when we had a series that was added together or subtracted, we could do the derivative of each one separately. So if we do the first one, the derivative of 50L, with respect to L, and then the rest. See, I finished writing it out there for you. So we have the first one is going to be 50, because that's a constant times a variable. The variable happens to be L. We're taking respect to L. So 50 comes outside. DL, DL cancel. We get 50. So the first point of this derivative is 50. Then we go to the next one. And 30 comes outside. So it's DL squared over DL. And finishing that out, you see that we have 30 comes outside of DL squared DL, and minus 1 comes outside of DL3 DL, because 30 and minus 1 are constants and they're just multiplied by, so it doesn't change with A, or with L, as L is changing. So let's simplify. If 50 is simple as we can go. Now we have 30 times something here, but what is DL squared DL? It's 2L. So 30 times 2L. And then we have minus 1. And here we're going to have 3L. And then remember the power, 3 minus 1 would be the 2. And we see in the end that we have marginal product. Change in quantity over change in L is the marginal product of labor. Q is the total product of labor. And we have an expression, one which I gave you. That's how we got it. Now, average product of labor is Q over L, and average product of labor, being Q over L, is 50, because let's go up to the very top line, 50 times L, we're going to divide that by L, we're left with 50. 30 times L squared, we're going to divide that by L, we're left with 30L, because L squared over L is L, minus L cubed over L, that would be L to the third power over L to the first power, and the difference is L squared. So we now have total product that we started with, marginal product, and average product. Now I can go back to my Excel and I can take each of these equations, which I already gave to you. This is simply how do you get there? So let's take a look at one of the most cool things in using the calculus. And again, we can do this in Excel as well. We just can't do it with the same level of precision. But we're going to find out where you get some pretty good numbers, which should tell you that the Excel is a fair approximation, a pretty good approximation. But the math process here is going to be more precise. Now, you're not going to have to do both of these. You're not going to have to worry about both of these, and you may not have to do this kind of thing at all. But one of the questions you do have to answer is how much labor should I hire in order that I'm a profit maximizing firm? I want my best position. What is my best level of labor? I have to do optimization. Well, I'm not answering that question because I'm trying to follow the math we've done up to this point. We have to put a number of other things together, which we will do in the Excel and talk about that a lot. But look at the average product curve. It is a convex from above, concave from below, quadratic form. And if you look, the marginal product curve passes right through the maximum point of the average product curve. How do I know where that is? Well, I just looked at the table and it's approximately 11. How would I know that it was exact? We optimize. So how do we optimize? Well, first thing, you understand a derivative is a slope. The slope of the average product curve back here is positive and upwards, upward sloping. The slope over here at this point, we'll call that point B, and we'll call the first one point A. A has a positive slope, B has a negative slope, but the point we're interested in has a zero slope. So here we're using calculus. We know it's a slope, and our problem hinges on at what point of labor is the average product curve maximized. That is, where does the average product curve have a zero slope? So taking the slope, and I set up dAPL, the derivative of the average product with respect to labor, is equal to 0, will imply or will give us the labor, the amount of labor, for which average product is maximized. So let's actually do the derivative. And that derivative of the expression of the average product of labor schedule is equal to 30 minus 2L. I didn't go through those steps, but I've done that before up to this point, and I hope you can see how that worked. Now let's set it equal to 0 and see if we can solve for L. Well, that would be minus 2L, because I'm going to subtract 30 from the left-hand side, and I'm going to subtract 30 from the right-hand side, and then I'm going to divide both sides by minus 2. Okay, I noticed a error, so I backed up here. I wrote down the parameter wrong. It's 20, not 30, and I did that on the previous screens, although from a math point of view, it didn't make any real difference whether it was 20 or 30, but here, because I'm actually referring to the graph and so forth, it does. So, my apologies, back up to average product of labor, it's 50 plus 20L minus L squared, and we're going to take the derivative, last line here I'm working on, of the average product with respect to L. We're going to find where that slope is equal to 0. So we're going to solve this and set it equal to 0. And then we're going to solve for L. So how to take the partial derivative of this? You get three different terms, add it together. The derivative of a constant is 0, doesn't change. The derivative of 20L with respect to L is 20 times the derivative of L over the derivative of L. Those cancel. Derivative of L squared, I've already taken the minus here. The derivative of L squared is 2L. And we set that equal to 0. And it's real easy to see that we're just going to take both sides here. 20 minus 2L equals 0. And we're going to subtract 20 from both sides. Okay? And we're going to divide by minus 2. So I'm going to subtract 20 here. And I'm going to subtract 20 here. So that these terms go to 0. And then I'm going to divide both sides by minus 2. And I'm left with L and 10. That point is exactly 10. So I hope this helped. That's a little bit of optimization. We can do the same sort of thing and optimize in any expression, including a profit function, maximize profit, a cost function, minimize cost, and it's all exactly the same process. So I hope you've borne with me at this point. Again, this whole video is optional. It's to help you understand more deeply what's going on to the extent that that's something that you find valuable. So I could have stopped the video right there and been pretty happy with what I did. I certainly didn't prove profit maximization rules or any of those sort of things. It would take much, much longer. But if you're still with me, I did put a formula in the slides which could kind of throw you a little bit. And I talked about marginal rate of technical substitution. So here we go. What if in the long run capital is variable? And we could do this in the short run with two different types of variable factors, such as unskilled and skilled labor. But the graph over on the right talks about isoquants. All right, what are they? I can combine labor and capital in different quantities, and I will be able to produce different levels of output. Now, this shows a very, very general case, which says that I can use a little more labor and a little less capital and produce the same thing. For example, showing up now as green dots, I can use very little capital and a lot of labor, K0 and L0, or I can use a midland level of capital and labor, or I can use a lot of capital and very little labor. And in every case, I produce the same quantity, therefore the word isoquant, which is 100 units. I can do the same thing for 200 and for 300. But it shows the ability to combine labor and capital in different levels. Now your firm may look different than this. This is a very general picture. If you have a fixed proportion production function, for example, UPS, it's one driver, one truck, then these isoquants look very different. They look like right angle turns because you can't buy two trucks and one driver or two drivers and one truck. But this is the general case. So the output is a function of labor and capital is now variable, as I said. So we're going to maintain that the marginal rate of technical substitution is a negative number, the change in K over the change in L. A change in K, that's on the vertical axis, change in L is on the horizontal, so that is a slope. And if you look at the isoquants, they all have negative slopes. And the marginal rate of technical substitution would be very high at K2 and L2, and it would be very low at K0 and L0. So here's the equation I wrote, or most of it. What I actually put on in your notes is now equal to 0. Why? Because if dq is equal to 0, then that's an isoquant. That's actually the formula. Now, telling you exactly how that calculus expression shows up is well beyond what we need to know. But it does say something here very particularly. It uses a concept, and I got to create a little mistake here. Hang on. So the mistake is fixed, and I've written a couple things here. The partial derivative is the expression where I'm using what looks like a 2 or actually some kind of a script d, which is really what it is, and a derivative which uses the more bold d. Now, the partial derivative and the derivative, I've written here the change in Q over change in L in both cases. The difference is the partial derivative is how much quantity changes when L changes, holding everything else constant. Ceteris paribus is at the heart of economics. We always look at things holding something constant. But the derivative doesn't hold anything constant. It looks at the total effect, dq dl. So we didn't have to distinguish before because we have an output function that only has L in it. Everything else is automatically, by not being in the equation, held constant, right? But now our equation, our Q, is a function of labor and capital. So maybe it's cubic in both, and it's all multiplied together. Maybe it's very complicated. Could be. But this is what we're looking at, that the dq, the first red line, the total derivative of q, not with respect to anything, but what is the total derivative? It's made up of the following. The first term is the change in quantity as labor changes, holding capital constant, times the actual change in labor, plus the change in quantity when capital changes, holding labor constant, times the actual change in capital. So let's remove all of that and get back to our equation and see what we can find out. So we're going to say dq is equal to 0, so we have two terms here, and we can rearrange those terms, right? So as soon as we rearrange those terms, we're going to have this in a position where we can actually see something that's going on here. Remember, the slope is minus dk over dl. So let's reorganize this expression to see, and here it is. A little bit of reorganization, and you write this. And you say, well, where do the marginal products come from? Well, what is the marginal product of labor? It is the change in output when labor changes, holding capital constant. It's the short run change. It's what our marginal product is. Well, what is the marginal product of capital? It's just the opposite. It's hold labor constant and figure out what that is. So just as labor has varying productivity levels, so does capital. You can buy so much capital that your marginal product goes negative, and that's not a good position to be in. You're so overcapitalized, your business will fail, just as you could be under using I'm sorry, I was thinking of something else. You could be using so much labor that you've also you got such a large wage bill you can't make a profit at all. So the trade-off then is between MPL and MPK. So where's the secret sauce in this? Well, here's the secret sauce. In blue, equation 1 is the cost function. Wages times labor plus rental rates times capital. That is, W is the price of labor, R is the price of capital. And we rewrite that in terms of K as a function of L, so we can graph it. You can see the blue line over there. And K is equal to C over R, which is a constant, we don't care about it, minus W over R, which is the slope. To produce optimally at any point theoretically, but I drew one particular point where the isocost is parallel to the isoquant, requires that the slope of the isocost curve, minus W over R, be equal to the slope of the isoquant curve, which is minus PL over MPK. Rearranging it here, is indeed the secret sauce. How do you optimize two factors? You move them around until the productivity per dollar spent on both of them are equal. So if you can move a dollar from labor to capital because capital is more productive, then taking it away from labor, according to, on this isoquant, in order to produce the same item, will lower that marginal productivity or raise that marginal productivity, lower the other, and you end up with an equality. Spend money on your factors such that the productivity per dollar spent on each and every factor are identical. Turns out that's a pretty good point to be, and it's also very strongly related to the profit maximizing point for your firm. And that's all. We're going to stop here, and I apologize, this video is very, very long, but I hope it's helpful.